Today's video is on qualitative changes in equilibrium systems. So in the last note, we looked at some quantitative changes and we actually looked at some numbers. Today we're going to look at it more qualitatively, so in which direction the reaction will proceed without actually looking at numbers. So today's big topic is Le Chatelier's Principle. This is a big, important topic, and it's going to keep coming up for the rest of the unit. So definitely pay close attention to this one and make sure that you understand how Le Chatelier's Principle works. So first off, we have to know that temperature, pressure, and changes in concentration affect equilibrium, and they each affect equilibrium in different ways. So if we increase or decrease the temperature or the pressure, or we add more reactants and increase the concentration, or add more products and increase the concentration there, those factors will all affect what happens to the equilibrium of that system, and those factors will change our numbers. So these factors will make the system undergo an equilibrium shift. So we're going to move the system at equilibrium. It's going to change and basically establish a new equilibrium. What actually ends up happening, the outcome, is governed by Le Chatelier's Principle. So here's the definition of Le Chatelier's Principle. When a chemical system at equilibrium is disturbed by a change in a property, so one of the ones that I mentioned up at the top, change in temperature, change in pressure, or change in concentration, the system will adjust in a way, and this is the key, that opposes the change. So we're going to do the opposite of whatever the change wants to do, and I'm going to show you what that means as we go through some examples. So any change to a chemical reaction at equilibrium causes the reaction to proceed in the direction that reduces the effect of the change. So let's go through some examples. We're going to start by looking at concentration changes, and then later on we'll look at temperature changes and pressure changes. So concentration. If we add a reactant or a product, the equilibrium is going to have to reshift and rejig itself and create a new balance. Okay? When we add a reactant or product, it causes the reaction to proceed in the direction that consumes the added substance. So again, if we consume that added substance, we're opposing the addition of that substance. That's what Le Chatelier's Principle says. The removal of a reactant or product, again, will cause the reaction to proceed in the direction that produces the missing substance. So if we take something away, we're going to want to oppose that and move the reaction in the direction that will make more of whatever we've taken away. So the opposite of what we've done. So let's check out this equilibrium. So as we can see, I've got a little, if you look down here, right at the bottom of my graph, here is the reaction that I'm looking at. So I'm looking at nitrogen and hydrogen gas combining to form ammonia. Okay, and at the bottom of my graph, this is time. Okay, so at time 0, here at the start of the graph, I've got 3 different substances, and they're all at equilibrium. Okay, now you notice that the concentration is not necessarily equal. Okay, the concentration here is about 0.5, here is around 2, and here is around 3, and it doesn't necessarily correspond to the coefficients. Okay, because my N2 is actually 1, my H2 is actually 3, and my NH3 is actually 2. So the N2 is technically a little bit off. So the concentration has actually nothing to do with the coefficients, okay? But the system is at equilibrium. How do we know that? Because the concentrations of my reactants and products are not changing. They're staying the same as we go through time. It's staying the same as we go through time, and the H2 is staying the same as we go through time. So I've got a system at equilibrium. Great. If you wanted to, I could make you calculate KEQ for this system. Okay. Now we're changing it up. So this is what's new for today. Let's say after, say, 1 minute of this reaction, I add more nitrogen gas. So what is that going to do? It's going to increase my concentration of nitrogen gas. Now instead of only having 0.5 moles per liter, now I've got around 1.5 moles per liter. So I've added in reactants. I've added in N2. Now what's going to happen? The equilibrium is going to have to shift again. And we're going to have to shift in the direction that will consume up or eat up or get rid of that added reactant. So because I've added N2, Le Chatelier's principle says I'm going to have the reaction happen to get rid of that extra N2, so do the opposite of what I've just done. So what's going to happen? The equilibrium to get rid of N2, if you just look at the bottom, at the reaction for now, to get rid of N2, I've got to make the reaction shift towards the products. If I want to get rid of more nitrogen, I've got to make more products so that I'm making ammonia and my nitrogen concentration can decrease. That's exactly what's going to happen. That's what Le Chatelier's principle is saying would happen. So when I do that, what happens to all three substances? Well, you can see if I'm starting to make more NH3, my concentration of N2 starts to fall a little bit and then eventually plateaus again. What's going to happen to my H2? It's also going to decrease. So here you can see up here, I'm starting to decrease it and then eventually it's going to plateau. What happened to my NH3? Oops, sorry. Oh, shoot. There we go. What happened to my NH3? Well, because I'm making more products to get rid of the N2, my products actually here went up and then eventually plateaued. So that's basically what's happening in the graph. You add one thing or two things or whatever it is, the reaction is going to proceed to basically do the opposite of whatever you've done. So when I add N2, I shift towards the product side. That's my equilibrium shift. I make more NH3, and I make less N2 and H2. Here are some more examples. So let's look at the first one. CO2, H2O gives you H3O plus and HCO3 minus. What would happen to this if I increased the acidity? So if I'm increasing the acidity, I'm changing the concentration of one of my substances. Which one am I changing the concentration of? I'm changing the concentration of my H3O plus, and I'm making that go higher, right? Because remember, that's your indicator of an acid. So if I make this go higher and I add more acid, what will happen to the rest of the equilibrium? It means the equilibrium is going to shift towards the reactant side, and I'm going to make more CO2 and more H2O. It also means that my concentration of HCO3 is going to go down. So all those things are going to happen. So if I increase the acidity, it will cause an increase in CO2 as well as H2O and a decrease in HCO3. Okay, let's ask you another question. Let's look at the second example. What would happen if I increased my SO3? So if I increased the reactants, what would happen? If this gets added, what'll happen? I'm not going to make even more of it, so I'm going to actually shift towards my product side in this case. And what's going to happen? I'm going to favor my products. I'm going to make more SO2, and I'm going to make more O2. All right, now I'm going to go through a quick little slide about explaining this based on the kinetic molecular theory. So let's read through these points. Why does this happen? Why do we see this shift? Well, when I add reactant, if I have more reactant, it means I have more chances of more frequent collisions because I've got more of them there. And that increases the rate of my forward reaction. I've got more reactants, they're all bumping together, and I'm making more products. So I've increased the rate of the forward reaction. The rate for the reverse reaction does not increase immediately. Therefore, your forward and reverse reactions are not equal. But eventually, the reverse reaction rate, because I'm making more product, the reverse reaction, those products are going to bump together and make the reactants again. So the reverse reaction rate eventually increases as well as you get more and more product formed. All right, let's take a look at temperature changes. Heat usually heat always evolves in an exothermic reaction. That means heat is released in an exothermic reaction, and it is absorbed in an endothermic reaction. Okay. Now we haven't done our energy unit. Usually we've done the energy unit between now or by now, but we haven't done that. That's not a big deal. The way we represent an endo or an exothermic reaction is where we write the energy in our balanced chemical equation. So it says here, Changes in temperature will have the same effect as changes in concentration. So I've given you this example here with N2 and O2. And I've got this adding heat here. Now because I'm adding heat in at the beginning, that heat is getting absorbed by the system in order to make my products. That means whenever you see energy in the reactant side, it means it's endothermic. Okay, if I wrote 180.5 over on my product side, that would mean it's exothermic because that heat or that energy is being released in the products. So here we have an endothermic reaction. If the mixture is heated, so if I add more heat, then the equilibrium shifts towards NO. So if I add more of this energy here, I'm going to oppose that by shifting the equilibrium that way. I'm going to make more nitrogen monoxide. If I cool down the system, so if this comes down, the equilibrium is going to shift backwards. Okay, there's another example of this. If you want to check out your textbook on page 454, it's figure 8. You can check it out. It's basically the same thing, but it just gives you another example. So you can check that out. And if you have questions about it, for sure let me know in class. Side note, the value of the equilibrium constant, that's your KEQ. That will change because an equilibrium constant is only constant at a specific temperature. So if I add heat, I've changed the temperature. If I take away heat, I've changed the temperature. My KEQ value will change. Why? Because of all these shifts that's happening, it's going to change all my final concentrations. And we all know that we need our concentrations of our products over our concentrations of reactants to calculate KEQ. So if these concentrations change, obviously my value for KEQ is also going to change. Okay, here's another explanation of why we see this effect with temperature change based on kinetic theory. So we're looking at an exothermic reaction in part A and an endothermic reaction in part B. For an exothermic reaction, if you see energy is on the product side, what happens if we cool it down? Initially, the forward and reverse reactions were both going to be a little bit slower, but the reverse rate is going to decrease more because that's the side. So if I'm going this way, in order to go that way, I need energy to make reactants. So if I cool an exothermic reaction, more products and more energy will eventually be formed, and we get a shift to the right. So if I take away energy, if I drop energy, eventually what's going to happen when it reaches equilibrium, it's going to have shifted that way. If I cool an endothermic reaction, so here's my energy, if I decrease that, I'm going to want to replace the stuff that I've taken away. My equilibrium will shift to the left. All right, one more thing to go through. Gas changes, pressure changes, or volume changes, okay? When we're talking about gas, pressure, and volume, this only works for gaseous equilibria. So that means all of the entities have to be in the form of a gas, okay? Basically what happens if we decrease the volume or increase the pressure, it causes the reaction to proceed in the direction of fewer number of moles of gas, reactant, or product. So whichever side, reactants or products, has fewer moles, that's the side that's going to be favored. Why? These occupy a smaller volume, so if I have fewer numbers of molecules, it occupies a smaller volume, and that relieves the stress of the added pressure on the system. If we do the opposite, if we increase the volume or decrease the pressure, it causes the reaction to proceed in the direction of greater number of moles of gas. Again, because there's more room to move around, we can have more molecules. So the example I'm going to give you, N2O4 gives you 2 NO2. If we increase the volume, we're going to drive the reaction to the right, because if we increase the volume, we're going to drive the reaction to the direction of greater number of moles. That's this way, because there's 2 moles on this side and only 1 mole on that side. If we decrease the volume, I'll do that in blue, the reaction is going to shift this way because we're going to shift to the side with fewer number of molecules. There's an example in your textbook if you want to have a look. I also have a video attached here. Let's see if it works or not. Oh, it worked earlier. Let's see. Oh, no, I do not. Of course. Why would that be easy? Okay, let me pull up that video for you guys really quick. Here we go. So here's this video. So I'm at a certain pressure here. What I'm going to do is I'm actually going to compress. So I'm decreasing the volume and at the same time increasing the pressure. Watch what happens to my molecules. So right now, if you take a look, I've got many, many NO2 molecules, and this one here, my N2O4, and so I've only got 2 molecules of N2O4. When I compress it, I'm going to make more molecules of N2O4 because in the whole long run gives me fewer molecules, and that decreases the pressure of the system. Okay, so let's go back to here. And we'll go on to the next slide. We're almost done. So how do I explain these volume changes using kinetic theory? When we decrease the volume, the forward and reverse reaction rates increase, but the rate of the forward reaction, at least in this example that I've got written up here, is going to increase more because there's more particles. So when I decrease the volume, I've increased the pressure. I've got more particles here. They're going to collide more and shift the equilibrium that way. So I've shifted to the side with fewer number of molecules or fewer number of moles. Lastly, changes that do not affect the position of equilibrium. If we add a catalyst, what it will do, it'll decrease the time required for the reaction, but won't affect the final position at equilibrium. It lowers the activation energy, which we haven't learned about, we'll learn in the next unit, for both the forward and reverse reactions. Basically makes the reaction easier to happen, but it will not affect the final equilibrium. Also, the addition of an inert gas at a constant volume, and you will see some questions where this happens, this will change the pressure in a gaseous equilibria, but because the gas can't react with any of the other gases, there will be no change in equilibrium. So the presence of the inert gas changes the probability of successful collisions for both reactants and products equally. There's no change there. So that's all for today. We will go through some more examples in class as per usual, and hopefully you've written down any questions that you have and we can go from there.